All right, hello everybody. Welcome to the third part now of the video for section 2.1. A lot of stuff to cover in this section. And yeah, let's continue on here. So let's look at identifying whether or not something is a linear function based on a table of values. Okay, so here we have two functions. Looks like we're calling them both f of x, which is probably not a good idea, but we did it anyways. And one of these functions, or one of these tables, represents the inputs and outputs for a linear function, and one represents a function that is not linear. And it is our job to figure out which one is which. Now, recall that one of the defining factors of a linear function is that it has a constant rate of change. And what that means, again, is that over any interval that we look, we'll get the same rate of change. So it doesn't matter if we look from, like, say, in this first function, like from the interval from 1 to 3, or 1 to 4, or 3 to 10, or 3 to 4, we should get the same rate of change if that's a linear function. Whereas if it wasn't a linear function, one or more of those rates of change might be different. Okay, so let's do some calculations here. So for the first one, I'm going to find the average rate of change over the interval 1 to 3. And remember, we calculate average rate of change just like we calculate slope. We do the difference in the outputs here. So I'll do -1 minus -5 over the difference in the inputs, so 3 minus 1. When we do that, I have -1 minus a -5, which will make a plus. So -1 plus 5 is 4. Over 3 minus 1 is 2. So it looks like we got an average rate of change of 2 there. Let's compare that to the average rate of change, let's say on the interval from 3 to 10. So if we calculate our rate of change here, and I'm using m, I should be using rate of change, but it'll be all right. So the difference in the outputs again, which is 13 minus -1, over difference of the inputs, so 10 minus 3. 13 minus -1, that gives us a 14. 10 minus 3 gives us a 7, so 14 over 7 is 2. So it looks like in both cases, we ended up with an average rate of change of 2. Okay? And I would bet that if we looked over other intervals, we would get the same rate of change. So it looks like that one there on the left may be the linear function. Okay, so I'm going to write, after I get this all erased, I'm going to write linear function? Question mark. Okay, so we think it's that one. So let's check some rates of change over the same intervals for the function on the right. So first we'll do 1 to 3. So our rate of change here, difference in the outputs, so 6 minus 1 over difference in the inputs, 3 minus 1, should be 5 over 2. Okay. Whereas we can also look over the interval 3 to 10 here, and if we do our rate of change there, we'll have 55 minus 6 over 10 minus 3. 55 minus 6 is 49. 10 minus 3 is 7. So it looks like we get a rate of change of 7 there. And notice that's different than the one we got over here, right? So it looks like the average rate of change is not constant on that function. So this is not our linear function here. So our original guess was correct. It is the one on the left. All right. Cool. So remember, linear functions have a constant rate of change. So regardless of which interval you look over, you should get the same rate of change. All right, so we're going to finish this up by just doing one more application problem involving linear functions. So here, we're told that at age 20, the maximum target heart rate when exercising is 170 beats per minute. And then at age 70, the maximum target heart rate is 128 beats per minute. And first part says, assuming that the relationship between age and heart rate can be modeled by a linear function, write an equation relating them. And as we've been doing in all the problems before, the first thing we have to do, find the slope. In order to find slope, we need points. Okay. And it looks like I have a 20 that corresponds to a 170 here, a 70 that corresponds to 128 beats per minute. And so before we write our points, we first need to think about inputs and outputs and what makes sense here. So does it make sense to input age and output heartbeats, or input heartbeats and output age? I think it makes most sense to input the age. So it's like 20 and output the heartbeats, so 170. So we'd have 70, 128. Can use this information now to find our slope. So we can do 170 minus 128 all over 20 minus 70, which then 170 minus 128, that would be 42, is that right? Yep, over negative 50, which I think reduces to negative 21 over 25, or negative 0.84. Leave it like that for now. Okay, so that's our rate of change, is negative 21 over 25. Which, let's also think about, does it make sense that that rate of change is negative? Well, since the maximum target heart rate is our output, as the input, which is the age, increases, what happens to that maximum target heart rate? Well, it goes down, right? So because of that, it makes sense our slope should be negative. Cool. All right. Glad we got that all squared out. Okay, so that's our slope. Negative 21 over 25. Once we have the slope, what comes next? Right, we need to find our vertical intercept. So that's step 2. Okay, and recall that we do that by choosing a point and our slope, plugging it into an equation, or the equation. So using f of x equals mx plus b here, since this is a linear function. Our slope is negative 21 over 25. Recall that it doesn't matter which point we use, so I'm going to use one where you input 20 and output 170. Okay, and I'm not going to work that all out exactly. I'll just tell us what the answer is here in a second. Okay, so we get the value for B should be 186.8. Okay, so now we have the value for B. We can plug that in with our slope into the equation here. The f of x equals mx plus b to write our equation. And actually, since we input age and output heart rate, I'm also going to change my variables here. So I'm going to have this be h of a, where h stands for heart rate, a stands for age, equals our slope, which is negative 21 over 25. A, since that's the age, that's the input, plus 186.8. And there is our equation, right? Cool. And the last thing, use that equation to find the maximum target heart rate of a person who is 33 years old. Well, they've given us an age. Age goes in for A values here, so we can do H of 33, give us negative 21 over 25 times 33, plus 186.8. So negative 21 divided by 25 plus times 33 plus 186.8. And apparently I don't know how to put things in calculators because I got an error. Okay. So we get 159.08 is the maximum target heart rate. So, and that would also be beats per minute, right? Because those are output units. I'll also say, believe it or not, the person speaking here is 33 years old. And my maximum target heart rate, I hope, is above 160 because I hit that mark often. But that's neither here nor there. Okay, so there's our answer. All right, that's all for now. Thank you all for watching.